I hope I've gone live. All right, yes. So I think as you can see from the title, and the title is complex analysis, of course. So complex analysis. And the topic we'll be starting with is called complex numbers. Complex numbers. And of course, that's the most basic part. And if we're talking about complex numbers, then we're simply just not giving a prerequisite or a pre-conceptual description of what's necessary for complex analysis, but also a complex number in itself is very useful in all levels, particularly even at schools and colleges alike. You need complex numbers everywhere eventually, and I think so. I intend to show you the fact that it is, in fact, a very useful concept. That's why we are doing this. We're doing this live stream, so I hope everybody gets benefited by it. If you have any questions, just redirect it in the comment section, and from time to time I'll try to address them. Okay, so I hope you can see everything, hear everything clearly. If you also have any problem understanding any of it, you want me to address it, just let me know in the comment section. Okay. So is it streaming still? Yeah. Okay. So everything will be recorded. I'll publish them afterwards. Everything finishes. So let us dive straight into it. This is our topic for today: complex numbers. All right. So why complex numbers? Why do you talk about them? What is our interest in them? Let's give ourselves a bit of background. Complex number were not invented, right? Nothing in mathematics, almost anything in mathematics is a language that is used to express our nature, okay? And one of the goal of the mathematics or mathematical sciences is to use it in more and more abstract languages so that we can encapsulate more sections or segments of science and of nature. And eventually mathematics has gone out of the necessity part and became itself a viable subject, which then motivated to give rise to other sections as well. So complex number is falls into that kind of category where it was forced out by nature. Okay, so nobody had to we had to construct the language, of course, but it is indeed comes out of nature very elegantly. So one of the cases where it comes out is the solutions of the solutions of equations, the algebraic equations. So for example, excuse me. So motivation, right? So we're talking about motivation. So what could be an example? An example would be solve an equation. So solve an equation like x squared plus twice x plus 2 equal to 0. Okay? And when you're going to solve them, then one of the solution, okay, is like x equal to 1 plus square root of minus 1. Okay, now we know real numbers as they're defined cannot be squared and spits out or give off a negative number. That just cannot happen. You take two negative real numbers, multiply them, gives out a positive number, or square them, gives out a positive number. If you square a positive number, of course it's going to give out a positive number. So therefore, negative number inside the square root were not permitted. We simply didn't know the interpretation. Okay, so therefore it's a big no-no. And so it is a very I would say a banned thing, a prohibited thing. All right. I'm sorry, the analytics. All right, so and then this is just one example, right? So such numbers couldn't be found in nature unless in cases like this. But they at the beginning, of course, you'd just throw that away, that solution, and you'd say there is only one solution. But eventually what we've learned, there is a beautiful mathematical structure that requires the use or the mention of this type of solution for the sake of completeness. So for example, if this is one of the solutions, then we know that another solution, equations of this form, which is of second degree algebraic equations, ought to have two solutions, and in a lot of cases they do, but in some cases they don't. So the question is, when do they have two solutions? When do they have one solution? And it is solved beautifully if you adopt this convention of complex numbers, because then you notice that if you allow solutions like this, which we call complex, to occur, then all second order equations, all second degree equations, algebraic equations, have two solutions, right? So that is mathematically much more powerful statement than just to say, okay, sometimes there is one solution, sometimes there is two solutions, sometimes there is no solution. Okay, so that's why eventually we allowed complex numbers or imaginary portions. This would be the imaginary portion to exist, and later we found out their interpretations, and we found out the fact that they are indeed useful and they are naturally occurring in a lot of cases, especially in modern physics. Things like quantum mechanics uses a complex number very elegantly in all the cases. In one way or the other, of course, people have tried and found out ways to sort of avoid the use of complex number, but nevertheless, as you'll notice, that complex numbers are integral part of doing things, and it makes our life a lot easier. Okay, a lot of chats. Now let's get into the actual science, the actual uses. So this thing is called the imaginary unit. So a second. It's called the imaginary unit. Okay, and it is denoted by this symbol I. So I equals square root of -1. You might say, what if we have square root of -2, right? So notice, if we have square root of -2, we can write it as square root of -1 times square root of 2. The square root of 2 is a real number, and you multiply with them with the imaginary unit, and that becomes square root of 2 times I, and that shows that you can express all these imaginary numbers or complex number with the help of this symbol I. Okay, And what's the property of I? Of course, I squared equals -1. So that is the definition, I would say, of the imaginary unit. Okay, definition of I. It's just naming something, right? The word that's used is, I think, nomenclature. It's a mouthful word, but it's just a device to denote things, nothing else. All right. Okay, so that's that. Now, of course, the imaginary numbers are not an isolated stuff. They occur frequently, just like we have seen here. They occur frequently with a real part. Okay, excuse me. They occur with a real part, and they're written plus the imaginary unit or something times the imaginary unit. So what's a complex number? A complex number, usually we denote numbers with x, right? Complex numbers are denoted with z. So complex numbers, what are they? Complex numbers are any numbers of the form z equals a plus, so a is the real part, times I times b, where b is also a real number. Okay, so a comma b are actually real numbers. As you know, we write r, this double r. This font is used to describe the set of the real numbers, and then of course I squared equals -1. So that is the definition of complex number. Any number that can be written in this form is actually complex numbers. Okay, this part, I should say, this part is called the real part. Real. And this part is called the imaginary part, the whole of it. Okay, even though b is real, when b is multiplied with some imaginary unit, which is I, it's called imaginary part. Okay, so if we have to write real part and imaginary part separately, what we do is we write real, re, of z, and it's like a function, it spits out this number a, and we can write imaginary of z, that spits out the number that is in the imaginary part, the real number in the imaginary part. So not ib, but rather b. Okay? Okay. A complex number which has the real number, a real portion to be 0. Okay? So let's say if a is 0, then z equals ib is called the pure imaginary form. Okay, pure imaginary form. All right, so I'm gonna give it a separate color. All right, pure imaginary form. Okay, so two complex numbers are equal. So let's say there is a complex number z1 that is equal to a1 plus ib1, and then z2 equals a2 plus ib2 are equal if we say, okay, so let me phrase it better, are equal, i.e. z1 equals z2 if and only if both the real parts are equal and the corresponding imaginary parts are equal. So a1 equals a2 and b1 equals b2. Okay, fair enough. So this is about equality. So equality. Okay. We have terminology. Okay, we're going good. We're off to a good start. That means in the language of this functions, you'll say real of z1 equals real of z2, imaginary of im of z1 equals imaginary of z2 or im of z2. I hope everything is clear at this stage. There is no confusion, hopefully. I'll just simply move on. If you have any question, I'll check the comment section from time to time. Please do comment. And if you're a new viewer and you're interested in this kind of content, please do subscribe. And I'll try to arrange streams like this. Okay. The set of complex numbers is written with the letter C, but in double font. So when I'm writing C with a handwriting, I write it like this, just like the set of real number would be in this form, right? So it was written by ARR. So that's like using C, and as you can understand that clearly, notice the set of real number is actually smaller and a part of the set of complex numbers. So I'd say this, right? It's a part, it's a subset of the complex numbers. Now there are of course arithmetic operations. You can add two complex numbers to get a complex number. You can subtract a complex number. So let's do them one by one. You can see addition. Okay, so add, how to add, you say, all right, I add z1 plus z2, where z1 and z2 are of course in this form. So anytime I refer to z1 and z2, remember z1 means a1 plus ib1 and z2 means a2 plus ib2. So it's just a simple straightforward notation. There is no space or position for ambiguity. All right, so we can simply add two numbers, z1 and z2. So I have a1 plus ib1, and then I have plus, so this is one of the numbers, and then I have a2 plus ib2, this is another number, and then you can see we can just reorganize. We can add the real part with the real part, and we add complex part with complex, we add the imaginary part with imaginary part, right? So that's that. Same thing goes for subtraction as well. So add plus subtract. So all I'll have to do is replace this plus sign with a minus sign. So you have a plus here, but you have a minus here, and that brings the negative signs inside inside the operations in the corresponding terms, like the real and real will have a minus sign in between them, and the imaginary and imaginary will have a minus sign in between them. Notice this sign doesn't change. This one should not change. So it's a straightforward rule, right? Okay, and what of the next one? On the next one I have product, so multiplication. Let's see that. So multiplication. I should have written product, right? Product would be nice. So that would be z1, excuse me. That should be z1 plus z2, I'm sorry, z1 times z2. So I'm gonna write the product with a dot, and that will bring us to a1 plus ib1 times a2 plus ib2. Now, of course, it's a simple multiplication trick. a1 and a2 makes a1, a2, and then a1 times ib2. So we bring an I here, so I a1 I times a1 b2 plus, again, if you multiply these two, what do you get? You get 8i times a2 b1, and then I have I squared times b1 and b2. But remember, I squared is actually -1, right? So that becomes real. This part becomes real because -1 is real. So you bring the real parts together. You have a1 a2 minus b1 b2, okay? And then you put the imaginary parts separately, and you notice that the two terms in the middle do have I as coefficient, so you have to separate them. And what do you have? You have I times a1 b2 minus b1 a2, okay, or a2 b1, and whatever fashion you want to write them, that's fine. So that's the rule, right? Notice the real part already has, I'm sorry, it should be a plus. I wrote as a minus, it should be a plus. There is a negative sign in between the contributions from the real parts, but the imaginary part has all positive contributions. Now, the situation changes if we want to find out the rule for division or ratio of two complex numbers. So let's do that. So division of two complex numbers. How do I do that? Well, just divide. So z1 divided by z2. Of course, there's a condition. What's the condition? So let's see what's the condition. The condition, if you write a1 plus ib1 divided by a2 plus ib2, notice the number we have in the denominator is the z2, but z2 is, of course, a2 and b2 joined together in the complex form. And one of the things that holds strong in mathematics, even in this new field, is that you cannot divide a number by 0, because that doesn't mean anything. So in order for this to be fruitful, we'll have to ensure that a2 and b2 does not go to 0 simultaneously. That is not allowed, because otherwise the denominator would be 0, and then this ratio, this division, will just simply not make sense. It will become undefined. Okay, there is a way to simplify this into, so as you notice, is this a complex number or not? We don't know that because we haven't simplified it. And so how do we simplify it? The first thing we do is to multiply the numerator and the denominator with the conjugate of denominator. Okay, what do I mean? I mean, okay, so we have a1 plus ib1, and we have a2 plus ib2, but we have to be clever here. We have to be clever. So I will multiply. So if you multiply the denominator by a2 plus ib2, you'll still have a complex number, right? But if you use a negative sign, then something very interesting happens. What happens? I'll show you. But in order to keep things consistent, I need to multiply the numerator with the same thing. So ib2. And then this becomes a2 squared minus b2 squared minus I squared b2 squared, right? But I squared is -1. So negative and negative makes it positive. And lo and behold, on the denominator, we have suddenly a real number. In the numerator, of course, we need to be careful. We still have, so we have a1, a2 plus b1, b2. How do you have a plus? ib1 times negative ib2. So again, we have I squared, which is negative number, and you have a negative sign, so negative and negative makes it positive. Plus I Well, we can separate it, can't we? So I'll do that. So I'll just write this in separate lines. So still I need to have I, and I need to have the same denominator, which is a squared plus b2 squared, and then I have b1 a1 a2 minus a1 b2. Okay, so this now definitely looks like a complex number. So indeed, the ratio of two complex number is another complex number of this form. Okay, so these are some simple rules. Of course, the thing that we have done here is to we have defined the conjugation implicitly. So let's make that explicit. So conjugation, that's just an operation. Fancy name to say the fact that change I to negative I. So conjugation is an operation that takes I and replaces it with negative I. So let's see how that works if we have Z. And by the way, the conjugation is, so Z is equals A plus IB. Then its conjugate is written by Z star. A lot of the time it's also denoted by Z overhead bar. Okay. So depending on the textbook or the context you're using, or whatever convention your teacher or your instructor or your professor wants to adopt, just go along with that, and either one is fine. And that is given by A minus IB. So as you notice, only the change of the imaginary part changes. Only the sign of the imaginary part changes. The sign of the real part is unchanged. Okay, so I hope that is clear. Let's see if there is any question, any comment. The iota term. Hello Arnav, I hope you're doing well. Can you explain the iota term? I'm not sure what iota term means. Can you clarify that a bit for me? So I'll type it for you. So do you mean the term with I? Is that what you mean? Okay. Okay, so answer that. I'll come back to address it. Meanwhile, let me clarify some interesting rules. Rules that we already know already applies for normal numbers. So what are the algebraic rules for normal numbers? So rules for addition and multiplication. Okay, so addition and multiplication. So we have seen how to add or multiply two numbers, but how to go beyond that, right? How do multiplication and addition interact with each other? Basically, multiplication. So I have, excuse my spelling, multiplication, right? I think I'm very OCD about these things, right? Nevertheless, I'll make some mistake. No worries. To err is human, so it only makes sense that we make mistakes. I hope the audio is clear. The other day I was doing a streaming. Someone actually complained about all the background noises. I hope today the noise is a bit lower, a bit manageable, because I took some steps, some precautions. Nevertheless, there are room for improvement, which I would like to follow through. So what are these rules? Now, you might have seen these rules, but not know the names of these rules. But if you are in this field long enough, you are supposed to know about the names. The rule number one is that addition commutes. That means if you write Z1 and Z2, right? If you add these two terms, it's the same as Z2. z2 plus z1, right? Addition commutes. So this exchange of places means commutation. Exchange of places means commutation. The same thing goes for multiplication as well. So if you multiply two complex numbers, it doesn't matter in which order you multiply them. So z1, z2 equals z2, z1. Whichever number you put at the first or at the second, it's actually the same. So these are the rules that are called commutation, right? Let me write the name for those of you who don't know. I think most of you do know it, commutation, or most of you who will watch this will know it. But nonetheless, it's just good to remind ourselves from time to time. So that's commutation. Now, what about if you go from 2 to 3? What about, yeah, I understand if you exchange the places, then that's fine. But if you have three numbers, so for example, if I have z1 plus z2 plus z3, right? And so I'll write those numbers once again so that everybody understands what I'm trying to do. The question is, does it matter if we add these two numbers first or we add these two numbers first? Does that make any difference? Are they equal or not? And the answer is, of course, they are equal. And in fact, if you write without any brackets, without any parentheses, it's just all the same. z1 plus z2 plus z3. Okay, I say these z's because, well, I don't have to follow the American convention. But for Americans, I'll call Z if that is. But I believe I'm reaching for global audience, so I'm more comfortable with Z, if you excuse me. All right, so this is called. Who can tell me? This is called the associative law. Okay, associative. Associative. Okay, associative rule or associative law, and this extends to multiplication as well. So I can say z1, z2, z3, right? And if I multiply z1 and z2 first and then z3, it makes no difference if I multiply z2 and z3 first and then multiply z1. In any case, you can simply write z1, z2, z3, and everybody will be clear what you mean by that. There is no place for ambiguity. So both of these are called associative rules. Now, of course, as you notice, in both of these rules, I haven't interacted the addition and multiplication. Okay. The addition and multiplication are still separate. What if they start to work together? So I have I have z1 multiplied with the addition of z2 and z3. 2 plus z3. How about that? How does that work? So that works as z1 will be multiplied with z2, and then z1 will separately, in a separate term, will be multiplied to z3, and they will be added together. And this is called the distributive law. Distributive law. Is that clear? I hope it is clear. There is no need to memorize these definitions because this is the same in the real numbers as well. So you're all familiar with these. I don't think I don't want to reinvent wheels, right? So everybody, all of us are familiar with that. Okay, so hello, Yasho, money. Hi, how are you doing? Thank you for joining with us. You said yes. Okay, great. Okay, so I'm assuming when Arnav asked this question in the in the chat what he meant was this item. So let me just go back a little bit. Notice I is the imaginary number here, right? I is the imaginary unit. A complex number has a real part and an imaginary part, and the imaginary part is actually a real number times the imaginary unit. The imaginary unit is a square root of -1. Square root of -1 is called I, so I squared would be -1. Okay, and we're basically trying to learn the algebra of complex numbers right now. Eventually we'll see that we can do calculus with it, and there's a lot of interesting mathematical structures. In fact, the complex analysis or complex calculus is so rich in structure, it's unbelievable. Okay, that's actually my goal, is to show you these interesting things through the live stream. But for now, I'm going to start easy, and I'm discussing the complex numbers, which in itself is a very important topic for a lot of people, and that's my focus right here. Okay, so if you want to see an example, I can just quickly give you some numerical examples. Numerical example. Let me give it a different color. Okay, that's great. So number one, so z1 equals 2 plus 4i, and z2 equals -3 plus 8i. And if I want to add them, okay, let's plug in. So if you want to add them, so z1 plus z2, I take the two real parts, which is 2 and -3, and you add them. If you add 2 and -3, it becomes -1. And if you add the corresponding imaginary terms, there is 4i plus 8i, so we have 12i. Okay, very straightforward. If you want to multiply them, so z1, z2, you don't have to memorize the formula, just multiply as you would. So 2 times -3 is -6, right? And then we have 2 times 8i, which is 16i, and -3 times 4i, which would be -12i, and multiply 4i with 8i, that's 32 I squared, but I squared is -1, so we have -32. So -32 and -6 makes it -38, and then 16 minus 12 ends up in 4i. So that's the addition and multiplication. Okay. After that, I think everything is clear. There are simple definitions for the sake of completeness. So for example, we have let's say we say 0. So 0 complex number. How do I write it? It's basically the same as the 0 is the same in real and the complex part, but nonetheless you can write it as 0 plus I times 0, or 0 times I, that's fine as well. 0 times I. Okay, so that's 0. It is the additive identity. Okay, this is also called the additive identity. What do we mean by that when we say additive identity? Additive identity is basically if you add it with someone, that someone doesn't change. So if z is not equal to 0, that means it's either the real part is non-zero, or the imaginary part is non-zero, or both of them are non-zero. In any case, you have z is a non-zero complex number, right? Then by the way, it can be written as just 0. So then z plus 0 is just z. So as you can see, z hasn't changed. That's why it's called the additive identity. Which number, if you multiply a complex number with, doesn't change the complex number? Well, of course, there's the 1. That's the same in the real number system as well. Okay. Okay, so yeah, sure. Yes, it is indeed I is indeed the square root of -1. Can you take the complex geometry too? Of course, I'll take complex geometry. So this will become a series. Please come back and look for the saved. It's difficult for me to right now to solve complex geometry. I'm hoping you are asking for the geometry of complex numbers. Okay, so if you mean geometry, I'm writing it in the comment as I'm typing, so that's why it sounds like this. If you mean geometry of complex numbers, then yes. Okay, so I hope you'll continue to join the streams and find out to be useful. As I can see, there's some ups and downs in the network, creating some problems in viewing. So it's probably a network issue, but nevertheless, I am continuing to stream, and I hope everything I say in here will be stored, so that when you come back and want to check it out, then you get everything together, and so there is no problem. Okay, so that's 0, right? Now, then there is something called unity. So unity is basically, as we have seen in the real number system, is just 1, right? So it's 1. Let's write 1, and 1 can be written as 1 plus 0 times I, and this is called the multiplicative identity. Multiplicative identity. Hopefully I'm writing the spellings correctly. Multiplicative identity, what does it mean? If you multiply any number z with this number 1, doesn't matter whether, because we know the complex numbers are commutative, and so that should be just z. Okay, that doesn't change anything. If there is an operation, right, say a star operation, and there's a number in the desired set, in the set that we're working with, when starred with something else doesn't change that something else, it would be called the star identity. For example, if 1 doesn't change z through multiplication, that's why 1 is multiplicative identity. It's that simple, right? It's just terminology. Okay, it's good to be knowledgeable about terminology, even though sometimes it might be overwhelming. It's not a big problem. It's just a matter of familiarity, right? The more familiar you are with something, the easier it gets, right? That's a good thing about our human brain. Okay, we have talked about conjugation. So conjugation, I have talked about here, yeah. Okay, so this is another operation. Now let's talk a bit more about conjugation. So more about conjugation. Let's write this. So more about conjugation. So we define that conjugation. But let's talk about the usage here. So remember, if I say z equals a plus ib, then z star or z bar. Let me go with star. How about that? Star. Okay. Is a minus ib. All right. So you know what's most interesting? The interesting part is that z, if you multiply z and z star, first of all, if you add z and z star plus z star, what is that? That's just 2a, isn't it? Twice a. And it is a real number, because a is a real number and 2 is a real number. If you multiply two real numbers, it ought to give you a real number. Why is that? Because the imaginary part cancel each other. That's why it's a real number. Okay. if you multiply z and z star, what do you get? You get a squared plus b squared. That's an interesting observation that you must have. Why is that? Because I'm going to take you a bit out of the fold to sort of connect it to other branches, and it's very important for our intuitions to grow and develop like that. Z and Z star gives you a squared plus b squared, right? If you had a vector, so if we have a vector, if a vector, let's say, what should I say? Let's say capital Z, the uppercase Z. As a two-dimensional vector, it's written as a x hat plus b y hat. What is and this vector is corresponding to z complex number equals a plus I b. Notice z star is actually, which is a squared plus b squared, is really the modulus squared, modulus squared. Okay, because the modulus of the vector z is basically square root of a squared plus b squared. So there is a nice, beautiful correspondence, and we know vectors are geometric quantities. Vectors do indeed connect geometry to numbers. That's a very elegant way, and hopefully at some point I'm gonna give you another course on vector analysis in this channel. But for now, just this part of the knowledge will suffice. So vectors are directional quantities. Vectors are geometric quantities, and there is a beautiful connection between two-dimensional vectors or vectors in two dimension and z, right? The complex number z, and there is a correspondence and there is an exchange of language. As we shall see, this will help us to expand our ideas of complex numbers and the geometry associated with it into our discussion. Okay. Any other questions? Okay, no more questions. Okay, I'll continue to move on. How is the health of the stream? The stream is not strong. Stream settings. Okay, sometimes it's okay. I'm trying my best. The rest is on the network. Let's see what happens. Okay. Let's move on. Let's continue. So Z star is a very important part. It is also the real number. By the way, if you from here I can see that A can be expressed in terms of Z and Z star, and so can be B. So let's see that. Okay, so if you subtract Z star from Z, you get twice IB, right? Isn't that what we get? I think, yeah. So twice IB, and this is purely imaginary, Now from this relation and this relation, we can now safely write the real part. So also note the real part of Z, which is A, can now be written in terms of Z and Z star. So I can write Z plus Z star divided by 2. Isn't that interesting? Okay, how can I write the imaginary part of Z? Can I write that in terms of Z and Z star? Yes, we can. So Z which is b, which is written as z minus z star divided by twice I. Now, if you have I, right, I in the denominator, you can always bring it to the numerator with a negative sign, right? Why is that? Because you can now multiply the top and the bottom, the numerator and the denominator, both of them with I. And of course, in the numerator you have I, but in the numerator, on the denominator, you have I squared, which is negative 1. So I divided by negative 1 is negative I. It's that simple. Okay. So I hope that is clear. And if I want to do it in here, so what do? I can also write it negative. So I can write it z star minus z, right, divided by 2, and then I can write it as I. Okay, so that I can do as well. That's just an interesting bunch of tricks. And furthermore, if the sum of the conjugate is conjugate of the sum, and the product of the conjugate is conjugate of the product. Okay, so it is lagging sometimes. I'm very sorry for the quality of the network, Yash. Unfortunately, I wish I could have a better quality of network. So don't worry, all of it will be saved, and I hope the stream has everything in it. All right, so let's go back. I have the imaginary part. So as I was saying, so notice the sum of the so z1 plus z2. So I'd say moreover the conjugate of the sum. This is the conjugate of the sum. I'm sorry, it should be z2, right? z1 plus z2. So I'm adding two numbers and then I'm taking the star, I'm taking the conjugate. That's why I'm calling it the conjugate of this sum. Is the sum of the conjugate. That means if you take the conjugates first, if you do the conjugation of individual members first and then you add them, then it's the same. Okay, sum of the conjugate is conjugate of the sum. And same goes for products. The product of the conjugate is the conjugate of the products. So z1 star, z2 star. So the right hand side is the product of the conjugate, the left hand side is the conjugate of the product. This goes for division as well. So by the way, I can also put negative sign here, negative sign, replace the plus with minus. Doesn't matter, the rule is the same. And you can also do divisions. So you can divide z1 by z2, and then you can take the conjugate, or you can take the conjugate first and then divide it. Okay, and finally, this is interesting, trivial but interesting, is that if you conjugate it twice, so conjugate it and then conjugate it, right, it's also written as z bar over bar, right? Remember, bar is also conjugation, sometimes bar is used. It's the same as z. That means if you conjugate once and then conjugate once again, you get back the first number, you get the original complex number back. Okay, so it's a lot of fun until now. I hope you recognize that, dealing with the complex numbers. If you can do some comparison with the real numbers. There is a lot of similarity, but there is also a lot of extra structures. There are different structures. Okay, and that's what makes the complex number most powerful. Okay, it is amazing. to be honest, as you'll see as we go along. It is very useful, um, and in your life, it's one of the most useful and spectacular thing you can learn, um, uh, in mathematics and in physics, to be honest. So now, before going, this is where the content ends. Before going, what I'm going to do is I'm going to show you some examples. I'm show you some exercises. I'm sure a lot of you are students, and I can spend an entire day solving different types of problems. That is also an option. But just to give you some extra snacks, as you have very graciously and very kindly participated and commented in my video. And for those who in future are going to watch this video, they can also have something useful. So yes, I'm probably gonna deal with the exercises in future, but just for now, I'm gonna give you some interesting maths. So some exercise, right? Exercises. You can do it by yourself if you have a pen and paper ready. Just try it. So for example, let's say I have I, and I have like to the power 105. Okay, so what is that? Now, those of you who are already well versed in complex numbers will find it trivial, of course. But I want to show you a pattern. The most interesting way to discover the answer is to see a pattern. Okay, so solution. Okay, so I'm going to be a little bit elaborate. Please stay with me. I have some patience because this is useful. So I know that I squared is -1. I know that I cubed is I squared times I. Okay, but I squared is -1, so I can simply write as -I. So I cubed is -I. Interesting. If you say I to the power 4, what are you taking? It's I squared times I squared. But I squared is -1, so it's -1 squared, which is +1. Interesting. And then if you want to take I to the power 5, if you go one extra step, you'll notice you get I times I to the power 4. But I to the power 4 is just simply I. So from here, we interestingly discover a structure that is these four numbers: -I, -1, -I, 1I, right? They form a kind of closed group. And of course, it is a little improper of me to utter the word group here, because group does have a mathematical meaning, and indeed they form a group. But let's just think of this thing as a closed circle. Okay, so every time you multiply with an I, so you go from I, you go multiply 1 with I, right? So when there is nothing, there's just 1, and then you multiply 1 with I, you get I, okay? And then you go, you multiply I with I, then you get -1, which is I squared. Then you get multiply once again with I, which is I cubed, so we have -I, and then multiply with I once again, you have -1 squared, which is 1. Okay, so I'm gonna write that like this. So this is -I, this is this is just 1 plus 1, and it goes back to the circle once again. So let me select these things, make it a little bit more colorful. Okay. And then in each step, of course, I'm multiplying things with I. So multiply it with I, then with I, then with I, then with I. So it forms a nice circle of, or a nice group, a closed circle, closed group, when you keep multiplying this, right? So then, now for the structure. Notice if I have I squared, I get -1. But if I have I to the power 4, I have plus 1, and the cycle repeats itself. So the bottom line is, if you get I to the power 4n, 4 times an integer, you're supposed to get 1 back. So this is 1, considering 1 is an integer. Okay, 1 is an integer. All right, so equipped with that, if I have I to the power 4n plus 1, that means you multiply with 1 more I should get I. If you have I to the power 4n plus 2, well, I times again an I will give us -1. And I times 4n plus 3, I have -I. And the cycle repeats. If you multiply 1 more I, you go from here to there. Okay? So, can I write the power that has been given in this form? Yes, I can. I can write. So I'll just do it here. So 105 is basically 104 times 104 plus 1. Why did I write it like that? Because 104 is a multiple of 4. In fact, if it were 100, 4 times 25 would be 100, but then we have another 4. So I think it's 26, right? 25 gives the 100. Yes, 26. So 4 times 26 plus 1. Now I times 105 equals I times 4 times 26 plus 1. Which structure is that? This structure. So this is simply I. Okay. So similarly, I'll give you another example. Number 2. Let's have a small number. Let's have I to the power 11. How much is that? So that is I to the power, what is the closest multiple of 4? So it would be 8, right? So because the next one would be 12, and then we'll just go one step away. So it's 8 plus, so 8 is 4 times 2. 4 times 2 plus 3. 8 plus 3 is indeed 11. So which structure is that? This structure. We have -I. That is the answer. Now I can give you any number, any exponent, and you can still find out the answer using the structure here. Okay, so that's a way to add it. Yes, thank you very much. Thank you, Yash. I hope you don't mind me calling you Yash, for writing us in the comment section. Very nice of you. Thank you very much. I hope you'll stay with me in future. We'll continue this, and we'll do, hopefully I'll do a separate section for solving the exercise questions that will help you in your exam. So thank you very much. I hope I'll see you around, and